Okay, now we shall talk about the formation of images, sign convention and focal length formula. These three things will be covered in this class. Rules of image formation. Actually there is just one rule. Angle of incidence equals angle of reflection. You have to keep in mind this thing. Minimum 2 light rays are required to form an image, and see, I will show you. If I take a light ray parallel to the principal axis, it passes through the focus. We have done it. Again, here also I am using angle of incidence equals angle of reflection. Okay, so parallel light ray always passes through the focus. The reverse will also be true. If a light ray is passing through the focus, it will become parallel to the principal axis. What if I take a light ray passing through center of curvature? It will return. And the reason is because the angle of incidence for this light ray is 0. It is striking the mirror along the normal. It is just like this case in a plane mirror. It is striking along the radius, along the perpendicular, so it will return. Same way, if I take this light ray, this is also passing through the, it will also return the same way. If I take any other light ray, for example this one, so this is the normal, this is angle of incidence, this is angle of reflection. You can take like this. So keep in mind, a parallel ray will pass through the focus. A light ray passing through the focus becomes parallel after reflection. A light ray striking the mirror along the center of curvature, along the radius of curvature, or passing through C will return, because angle of incidence for this will be 0. Okay, and now using these rules you can draw the images for different positions of the objects. This also you have done in class 10th, but again I am giving you few examples and others you draw yourself. For concave I will give you just 2 cases. This is pole, this is F, this is C. Suppose the object is here, AB. So a parallel ray will pass through focus. If I take one light ray from center of curvature, it returns. I may take another passing through F and then it becomes parallel. I have taken these 2 rays, third one, even this can be taken, coming back. So the light ray which starts from A, coming back to A, starting from B, this is the point where these 2 rays intersect. This we call as image. So if you are looking from this side, this object appears at this point to us. Okay, that is what we mean by image. It is the perception of the object as perceived by our brain. So this is image and it is real because the rays actually meet at this point. Rays are actually going to form these images, right? This image particularly. So this is the real image. What about the size? It is smaller, diminished, it is between C and F, inverted. So inverted, real, it is inverted, it is real, it is smaller or diminished, and it is between C and F when the object is beyond C. If we bring it closer, at C the image size is same as of object. For object between C and F, image is formed between beyond C. Size will keep on increasing as the object is moved towards the mirror. There is one particular case in concave mirror. Which is different from all others. F, C, if I take an object here. So it is between F and P, between focus and pole. So one light ray parallel, it will pass through focus. And then one we can take along C. So if we look from this side, they are diverging, so they will never meet here. But looking from this side, it appears so A dash, B dash, this is actually the image and is virtual because the rays appear to come from there. They are not going to frame this image at this particular position. Okay, so this is virtual, erect and magnified. This is the only case in concave mirror when the object is placed between focus and pole that the image will be magnified. In all other cases it will be diminished. Okay, one case we can take for this is C. So again, I have taken one parallel ray, it appears to come from focus. Another ray I have taken moving towards center of curvature, so it is falling normally, so it will return. And here they intersect, so this is the image, A dash, B dash. It is erect, it is magnified, oh sorry, it's not magnified, it is diminished. And virtual. And this nature of the image makes this mirror very useful. It is used as rear view mirror in vehicles. Because of the smaller size, the view is enlarged. So very useful mirror. Here we may have inverted images, erect image, one particular case, but here the image is always smaller than the object and erect. Now whenever it comes to the measurement of distance, we will derive an expression for the focal length in terms of making it slightly bigger so that it is visible to you. We are doing it particularly for concave mirror, and that also I will take one particular case, but this expression is valid for both convex as well as concave and for all cases. This is F, this is C, and I am taking an object here. Parallel will pass through focus. Then one we may take through C, it will return, and one more we can take, okay, this. Angle of incidence equals the angle of reflection. Okay, here is the image, A dash and B dash. See carefully, I have taken three rays. One is parallel, this will pass through the focus, through C, it returns, and one is striking the mirror at pole. So this is the angle of incidence, this is the angle of reflection, it will pass through this point, all three rays meeting at this point. Okay, so this is the image formed. Now, this distance of object from the mirror, we denote it using a symbol B. We take it as a standard symbol. Distance of image, we take V from the pole. And this, we already know, this is the focal length, F to P. Now we will find out the relation between these three quantities, U, V, F. Distance of object from the mirror, distance of image, and the focal length. So we want to see if we are given the distance of object from the mirror, where will the image be formed? We can find out using an expression. Okay. And to measure the distances, we have to use proper sign convention. Sign convention means what sign should we use with these quantities, U, V, and F. So note down these rules. All distances are to be measured from P. All distances are to be measured from P. Distances, just one general rule which is applicable to all. Distances measured in the direction of incident ray are taken as positive. Distances measured opposite to the direction of incident ray are taken as negative. Now see here, the incident ray is left to right. This is the direction of incident ray, and we have to measure distance from P. So whether I am measuring the distance of F, I will start from P, P to F. Distance of object, P to A. Distance of image, P to A dash. So all distances are measured against this. So in this particular case, U is negative, V is negative, and F2 is negative. F for concave mirror will always be negative because this point will always be taken here. While for convex, we know the focus is on the right side. This is C, this is F, and if I take an object here and draw the ray diagram, parallel appears to come from focus, and another one through C, it returns, here is the image. Okay, so anyway, this is the direction of incident ray, and this is pole to focus, that's also in this direction. So F will always be positive for convex. For concave, focal length is negative, and this convention holds even for lenses. Concave lens, concave mirror, negative focal length. Convex lens, convex mirror, positive focal length. Distance of object will always be negative because object will always be wherever you keep it. Light rays will be moving from the object to the mirror, and U will be measured from the mirror to the object. So they will always be in opposite direction. U will always be negative. V, it depends. Concave mirror, there is one case when V is positive. Let's try to recall that. When the object is kept between F and P, image is found on the right side, so V will be positive. For all other cases, it will be minus. Here, image is on the right side, so V is also positive. U is negative, object on the left side. Okay. So this is distances along the axis. For perpendicular also, the rule says distances above the principal axis we will take them positive. Distance is below the principal axis, we take them negative. So here the object height will be taken as positive, image height will be taken as negative. And for convex, object as well as image, both heights will be taken as positive. Both of them are above the principal axis. Okay, so now let's find out the relation between these three quantities. Okay, start. And it's very simple, we shall be using the property of similar triangles. A, B, P. One this triangle and another triangle A dash, B dash, P. Take this set of triangle and then draw a perpendicular, and then again this point very close to this. So we will ignore that distance. If I take this as N, this as M, so M and P I will take same. Okay. This triangle A dash, B dash, F, and triangle N, P, F. So this triangle, and this bigger one, and this bigger one. See carefully. These two similar triangles, in similar triangles, the ratio of two sides is same. So I will be using this property. First for this, ABP, this bigger triangle. A dash, B dash, P is this one. So A dash, B dash upon AB is equal to A dash P upon AP. Okay? And same way for this. A dash, B dash upon AB. First let me write it NP. NP. This one and this one, right? So this is A dash F upon this by this is equal to this upon Fm. And NP is equal to AB. This is equal to this. So it means these two sides are same. Okay. So it means right hand side should also be same. This is equation 1, this is equation 2. Left hand side are equal, so right hand side will also be equal. Okay, write it yourself. A dash P upon AP is equal to A dash F upon Fm. A dash P upon AP is equal to A dash F upon FP. FP or Fm. M and P are the same. Okay, M and P. So AP or AM, FM I can write even FP. 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 You can make the changes here, or we can write separately. M is very close to P because we are dealing with paraxial rays. Okay. Now substitute UV and F with proper sign. A dash P is minus V. AP is minus U. A dash F, this distance. This is this minus this. So minus V minus minus F. See it carefully. A dash F is this much. This V minus F. FP minus F. Okay, now rearrange the terms. This minus cancelled and we have V by U is equal to minus V plus F upon minus F. So we have minus VF is equal to minus UV plus UF. Okay, or UV is equal to UF plus VF. Now we can divide it by UVF. It doesn't make any difference if we divide by a common term to all. This will be 1 by F, this will be 1 by V, this will be 1 by U. So 1 by F is equal to 1 by V plus 1 by U. By 1 by F is equal to 1 by V plus 1 by U. This we call as mirror formula. However, keep one thing in mind, it doesn't mean that F is depending on U and V. F is constant here. V and U will change, but F will not. V will change when you change it, U. For different distances of object from the mirror, V will change. U and V will be same for when the object is placed at center of curvature. Then the image is also formed at the center of curvature, so U, V are equal. F depends only on radius of curvature. So this expression does not tell about dependence of F on other factors, okay? And one more thing here, another quantity, magnification. Magnification is defined as the height of the image to the height of the object. This by this. Now again, use this property of triangle, one this triangle and another one this. So A dash B dash upon AB is equal to A dash B upon AB. Okay, again I have used the same set of triangles. So A dash B dash is height of image, height of object. I am using now the sign convention. A dash B minus B, AP minus U. So this gives HI upon HO minus V by U. So this and this, these two expressions will give us the size of the image and the position of the image. Magnification formula, and this is the focal length formula. So one we have done, one expression F is equal to R by 2, we derived it last time, and one is this, one is the magnification. Now in the next class we will try some numericals based on these expressions. Thank you.